Hello and welcome to the NISER Bhubaneswar lecture series on quantum chemistry by Dr. Arindam Ghosh of the School of Chemical Sciences, NISER. Today we will discuss linear harmonic oscillator, the quantum linear harmonic oscillator. By the word linear, we mean that we'll be discussing one dimensional case, so that this motion is going to be linear in one dimension. Before we go to the quantum one, we quickly see what a classical harmonic oscillator does. So in a classical harmonic oscillator, we have say one spring that is attached to one mass m, and this mass is oscillating about the equilibrium position x equals 0. So this is your x-axis, right? It might have certain amplitude, right? So the amplitude can be written down as something like a and minus a. So we are considering the fact that this mass is acted upon only the force exerted by the spring, and the equation of motion classically we can write it down like m d2x dt2 is equal to the force, which is minus kx. This force is known as a restoring force, particularly because the reason behind this is that whenever the mass is moving, it is going towards the positive direction, positive x direction. The force is bringing it down to the x equals 0, the equilibrium position. And whenever the mass is moving into the opposite direction, it is still bringing it back to the equilibrium position. In a way, it is trying to restore its position to this equilibrium line, and that is why this force is considered to be or is named to be a restoring force. And in this particular case, we are not considering anything else or any other force. For example, there is no friction, there is no damping, anything, and that is why this linear harmonic oscillator is also can be told that this is a simple harmonic oscillator, or SHO. There are many books where this linear harmonic oscillator is also termed as simple harmonic oscillator. Simple because we are only considering the restoring force and no friction or any other damping force, which makes this whole calculation much more complicated. So this is a simple linear harmonic oscillator, and we'll see that what happens in the classical case first. So let me just write down this equation in a slightly different way. So I have written down the equation in a slightly different way. We have got this k over m, the factor, which is written as omega square, and we know that in the classical case, this omega is the frequency of oscillation given by root over k over m, where k is called the spring constant, is given by m omega square, where m is the mass of this oscillator and omega is the frequency of oscillation. So this is classical equation. We know that this classical equation has a very definite solution. The solution is for the classical SHO is the x is equal to some amplitude a and a cosine function of frequency and time, a cos omega t plus phi. Phi can be some initial phase. It might be 0 as well. We can quickly check if this is a correct solution or not. So if we just do d2x dt2 of this solution, we get some minus a omega square, and then here cosine comes back, omega t plus phi, and that can be written down as minus of omega square into the same x. Therefore, the equation that the d2x dt2 plus omega square x is definitely going to be 0. So therefore, this solution a cos omega t plus phi is definitely a solution for this classical equation, and the potential v of x can be written down as a negative of integral of the force f of x dx, and we know that the force is given by minus k of x, so therefore this becomes plus kx dx, which is equal to half k some x square. As this is a definite integral, we should in principle use some constant v0, but as you know that this is a potential energy Vx, and any constant potential can always be recalibrated to 0. So therefore, we really do not need any constant over here. So let me just remove this constant. This Vx is equal to half kx square is good enough. We can write it down in terms of omega. This is equal to half m omega square x square. So this is our potential. So what we'll do is that we'll be using this form of this potential into our quantum system to solve the Hamiltonian, solve the Schrodinger equation for a simple harmonic oscillator, a quantum simple harmonic oscillator with this particular potential. And the potential, if we just draw it, it looks like something like this. So here is the potential Vx, and this amplitude A and minus A, as I have drawn in the last slide. And classically, if you consider that this classical object comes to a rest when it reaches the its amplitude, then this entire energy is potential energy. There is no kinetic energy at that particular moment, because a classical oscillator, when it goes to the end, it stops. So the potential energy is the total energy, and therefore that entire energy is definitely given by half ka square. And then when it goes back and then it crosses 0, the potential energy is 0 at that time. So therefore the entire kinetic energy is now going to be half ks square, and then it goes back and forth, and that is how it goes for a classical oscillator. Now if we have to solve for a quantum oscillator, the first thing that we should do is to write the Hamiltonian, and that is exactly what we are going to do the next, as the next step. The Hamiltonian H is given by, is equal to the px by 2m plus vx, and this is equal to, we can write it on this minus h cross square over 2m. We know that this piece x square by 2m will convert into minus h cross square by 2m, and d2 dx2, that is our potential kinetic energy operator, plus now we know the form of Vx, and that is half m omega square x square. So this is our Hamiltonian. We can put a caret on top of H to denote that this is an operator, and this particular Hamiltonian now is going to be plugged in into the time independent Schrodinger equation to solve the equation H psi is equal to E psi. Psi is a function of x here because this is the space part only. So this is the time independent Schrodinger equation, and we have to solve the Schrodinger equation as the next step. So here is the time dependent Schrodinger equation. I have rewritten this including the potential term over here, and I have just rewritten the equation slightly in a different way, and we can see that this is second order or homogeneous equation, but the coefficients are not all constants because we have x square over here, so therefore it is not a case of homogeneous second order differential equation with constant coefficients. Rather, it is the coefficients are function of the variable x, and therefore solution of this equation is going to be slightly more tricky than the previous cases that we have solved so far. And to solve this, the first step would be that we'll be defining two quantities alpha and beta this way. So let's define alpha is equal to m omega over h bar, and beta we define to be 2 m e over h bar square. And if we just use this alpha and beta into the equation takes this particular form. So d2 psi dx2. I must tell that the psi is always should be written as psi as a function of x, but I'm just omitting that particular factor. This is the bracket x for brevity, and let's continue with this equation. So this is d2 psi dx2 plus we have beta minus alpha square x square psi is equal to 0. So this equation takes this concise form using these quantities alpha and beta, and we'll be using certain property of alpha and beta later. For example, I'll be using the fact that alpha can never be equal to 0, because alpha 0 directly means that our omega is 0, because m is a constant, h bar is a constant. So alpha 0 directly means that omega is 0, and if omega is 0, then there is no simple harmonic oscillation going on, and we are not interested in that particular case. So we'll be using later this alpha is not equal to 0, but that's going to be much later. So the next step would be that we introduce another quantity. This time it's going to be a variable. The variable is q, and we define q to be equal to root over alpha into x. This directly gives me dq to be equal to root over alpha dx, or in other words, I can write down that this gives me d dx is equal to root over alpha d dq. So we'll be using this um, variable q rather than this variable x directly for the rest of the calculation, and at the very end of this calculation we'll bring back from q to x for the solution. But for the for several slides after this we'll be using q. So now, if this ddx is given by root over alpha ddq, then we need to find out d2 dx2, because that's the operator that we have to use in this particular equation over here as well. And so let's see how that turns out to be. So we get d2 dx2 is equal to alpha d2 dq2, and if we substitute this particular operator into the original equation, we get the equation takes the form alpha d2 psi dq2 plus beta minus alpha q square psi is equal to 0. This is considering that we have q is equal to root over alpha x, so therefore q square is alpha x square. Here in this particular case we had an alpha minus alpha square x square, so one alpha is left from here and the other alpha x square is replaced by q square, and that is why what we get is, instead of minus alpha square x square, we get minus alpha q square. And now we'll be using the fact that this alpha cannot be 0, and therefore we'll be dividing by this alpha that is over here. The reason I have already told that alpha cannot be 0, because if alpha is equal to 0, then the omega is equal to 0. There is no simple harmonic oscillations going on. We are not interested in that particular case. So the next step would be that I'll be dividing this equation by alpha, and we'll be getting the equation given by d2 psi dq2 plus epsilon minus q square psi is equal to 0, where I have introduced another symbol epsilon, that is given by epsilon is equal to beta over alpha. And now if we just use the values of beta and alpha that we have defined previously, we get that this quantity is going to be 2m e over h cross square multiplied by h cross over m omega, and is equal to 2e over h cross omega. So this quantity definitely is going to be a dimensionless quantity, because you have h cross omega in the denominator, which has the dimension of energy, and we have E in the numerator, which also has this dimension of energy. So therefore this epsilon is just a number, and this number is also not a very large number, because this h cross omega is the energy corresponding to the frequency omega, the frequency of the oscillator, and this E is the total energy of the oscillator. So they are matching quantity. So this epsilon is going to be a number, a small number, and we'll be using this particular fact that this epsilon is a number later into the discussion. But the first thing first, and now we have to solve this equation that we have got. The central equation is this now, and the way we'll be trying to solve this is that first we'll be trying to find the asymptotic form, meaning that when x is too large, what the form of the solution might be, because we know that when x goes to either plus infinity or minus infinity, q also goes to the plus infinity or the minus infinity, and we know that as the q goes to infinity, plus or minus infinity, the potential v of x or v of q, whatever you wish to write it, this is the same thing. This, well, it's not equal to, but rather it is approaching to infinity, and as the potential is approaching infinity, we know that the wave function, and when q is approaching plus or minus infinity, should approach to zero, because when the potential is infinity, then the wave function cannot be non-zero there. The probability of finding the particle where the potential is infinity should be zero, and hence we conclude that when v goes to infinity, that is when q goes to either plus or minus infinity, the wave function should go to zero, approach to zero slowly, not abruptly. Slowly it should go to zero. So that is the asymptotic form. Asymptotic form means the form of the solution, the form of psi when q is too large. And first we'll be checking that, the asymptotic form. And the asymptotic form that we'll be trying is going to be of this particular kind. Psi A stands for asymptotic, function of q definitely is equal to a some amplitude exponential minus q square over 2. So this is an exponential function. We have taken a q square instead of just q, because it is necessary that when q goes to either plus or minus infinity, the wave function should go to zero. So therefore we have to take a q square here. Just plus or minus q would not take the asymptotic form of the asymptotic part of the wave function to zero for both q is equal to plus or minus infinity. Now we can check this particular solution, whether this particular solution acts properly or not for the equation. So for that we have to first calculate the second derivative, but before the second derivative we have to calculate the first derivative, which is equal to minus a times q times exponential minus q square over 2, and then we can write down a double prime q is equal to a q square exponential minus q square over 2 minus of a exponential minus q square over 2. So we have two parts in the, we have the q and an exponential, so we have to differentiate both one by one. That's exactly what I have done, and this can be further be written as something like q square minus 1 into psi a. Now there is no doubt that psi a, the asymptotic form, goes to 0 as q goes to plus or minus infinity because of this exponential factor. But what is necessary to be checked is that whether this particular solution is a correct solution or not for this equation. So for that, what you have to do is you have to plug in this double derivative over here and this value of psi a over here, and have to check whether this particular equation is valid or not for very large q, the asymptotic form. So the original equation was, let it be written down one more time. Sorry, this particular thing should be corrected. The original equation is d2 psi d q2 plus epsilon minus q square psi is equal to 0. Now we need to check whether this equation is valid for psi a or not. And then what happens is that if we plug in the psi a in here, what happens is the double derivative has something like q square minus 1 psi a plus we get epsilon minus q square psi a, and that is equal to, we get the q square goes out, and therefore we get epsilon minus 1 psi a. Now here we use the fact that epsilon is a number, a small number, that a small number, and therefore this whole epsilon minus 1 is a small number, and therefore this equation is going to going to 0 as q goes to plus or minus infinity. That is because this whole thing is going to be behaving like psi a, because this is just a small number, and as this function is going to 0, so the whole thing is going to be 0. So therefore this equation, the left hand side is going to be equal to 0 when q goes to plus or minus infinity, and therefore in the asymptotic form, it simply means in the asymptotic form, this equation is validated by the form we have chosen. And let me write it down. This the form that we have chosen is equal to a some amplitude and exponential minus q square over 2. So therefore this form is going to be our asymptotic form. Now the question is, what is going to be the general solution, which is not only the asymptotic part, but also the part where q is not tending to plus or minus infinity. Q is 0, for example. So the general solution is the next step, and for that what we do is that we'll be writing the psi of q. I'm not using the subscript a anymore, because this is not the asymptotic part only, but this is the total solution or the general solution. Some amplitude a function of q. I'll explain what this function of q is all about, and exponential minus q square over 2, that is coming from the asymptotic part. So the idea is that the total solution, psi of q, is going to be slowly going to 0 when q goes to plus or minus infinity because of this asymptotic part, but the solution, total solution, will also include the functional part for q not tending to plus or minus infinity, and that is going to be hidden in this f of q that we do not know so far. We have to find out what the function f of q might be by putting this solution, this as assumed solution, input into the original equation here, and that is the next step that we'll be doing. But for that, again, we know that the first step is that you have to find the double derivative of this psi with respect to q, for which I have to find the first derivative first. So let me write it down the two derivatives quickly. Fine. So I have uh, written down the first derivative of psi with respect to q and the second derivative of psi with respect to q, and we have got this particular expression for the double derivative which we need to plug in to the solution to this equation over here, and the psi is just going to be replaced by this expression of psi here. This is the assumed expression for psi, and once we plug this psi and psi double prime into this equation, we'll get out of this equation a new equation involving f, and solving that equation we'll be getting the expression for f that we need to finally plug in here to get the total solution, because this the asymptotic part is already tested that it is correct. This is just the amplitude. The only thing which is not known yet is the FQ part, and FQ part is, as I told, is going to be obtained by plugging these two expressions into the equation and then solving that new equation of f involving double derivative and single derivative of f. So let's plug in that these two expressions into the original equation, and let's see how does it look like. Yeah, so this is the original equation that I was talking about, and I have plugged in the value of d2q, dq2, and the value of psi over here, and then we get these terms from this, the first, second, third, and fourth term coming from here, and the last two terms coming from this expression, obviously. And if we just think that this entered thing has to be 0 for all values of q, and as we know that this exponential factor is in general not 0 unless q goes to plus or minus infinity. For any general q, this expression is not 0, so therefore this entered expression has to be 0. That simply leads to the fact that the expression within this bracket is 0, and that is the next step, that if we just simply rewrite the terms within the bracket, we get the equation involving f as f double prime minus 2q f prime plus epsilon minus 1 f is equal to 0. Now this is the equation that we have to now solve to find out the expression for f, and that f will ultimately go into the whole expression of psi, and along with this asymptotic form it will give the solution for the simple harmonic oscillator, a quantum simple harmonic oscillator. Now the question is that how to solve this equation that I have written down in green. This equation cannot be solved easily. It will take a particular type of solution that is called as the power series solution, and the fact that we need a power series solution is that we have the q over here. That means again the coefficients are not constant, but the coefficient has the variable itself, and that's the reason we cannot solve it easily. We have to solve this using the series solution method, for which the first step is that we would like to write down the function f of q as an infinite series given by some ai, the coefficients, and a q to the power I. So the power series solution, this is actually a power series. This is a very well-known method of solving differential equations with coefficients where the coefficients are not constant coefficients, but they are variable coefficients. We try to find out the series by plugging this assumed solution into the equation. So again, the first step is that we should have the derivatives. So this is the first derivative, f prime, which is summation over I comes down, ai q to the power I minus 1, and the double derivative is going to be summation over I into I minus 1, this time ai q I minus 2. Now we need to substitute these f prime and f double prime here in this f prime and f double prime, and then we should get this equation that is in this form of f, and this is going to be in the form of this infinite series, and that's the next step. Now let's substitute these three things into this equation, and then we get the following. Okay, so I have plugged in the series into the equation. This entire term here, it came from f double prime. This term came from the term minus 2q f prime. Now if you just check, this f prime has the power q to the power I minus 1, but then along with this q, this power goes back to I, the I minus 1 goes to the I, and then the last term is coming, this term is coming is equal to exponent minus 1 f. Correct, this is obvious. So these are the three terms that were in the original equation, and now they are all represented by this infinite series of index I. So now in order to have this entire left hand side to be 0 for each and every value of q, the only possibility is that each coefficient for each power of q should be individually 0. So this is the obvious next step of a series solution of differential equation, that whenever we have a series on the left hand side which is equated to 0 on the right hand side, we equate each power or rather the coefficient of each power of q, the variable, to 0. So that is exactly we'll be doing. So let's try to find out the coefficients of different powers of q, starting from say q to the power 0. So the coefficients are going to be obviously when I equals 0, then the first term is not going to give anything. In fact, the second term is also not going to give anything, but rather only the term that is going to give us is this one. So q to the power 0 will come from the first term when I equals 2, because that makes it q to the power 0. So when I equals 2, then this becomes a2, and this is 2 times 1. So it's going to be, I'll be writing as 1 times 2, a2, and that is one coefficient corresponding to q to the power 0. Another q to the power 0 will come from here, because here there's nothing will come, because here if I equals 0, q to the power, it becomes q to the power 0, that's okay, but and this becomes a0, but because of this I equals 0 will not give anything, but here when I equals 0, so this gives q to the power 0, and I have got an a0 over here, and therefore I get two parts for this coefficients of q to the power 0, and those two parts are 1 multiplied by 2 a2 plus epsilon minus 1 a0, and that is equal to 0, because each and every powers coefficient, corresponding coefficient, should be 0. The next one is q to the power 1, and we can similarly check that when q to the power 1 comes, when this I becomes 3. So when I becomes 3, then this becomes a3, that's fine, and this is 3, and then this is 2. So I'll be writing 2 times 3 a3 as the first uh, part, and then q to the power 1 also comes from here. So this one I equals 1, then it's q to the power 1, and therefore this is a1. So 2 times a1 coming from here, and when I here also, when I equals 1, you got a q to the power 1, and therefore you get an a1 over here, right? And it's epsilon minus 1. So therefore these two terms are going to be combined into one, and then this is going to be another one over here. So this is exactly what I'm going to write down next. Let me write it down. So it is 2 times 3 times a3 plus epsilon minus 1 minus 2 times 1 a1 is equal to 0. Similarly, we can just calculate different coefficients. This is going to be 3 times 4 times a4 plus this is going to be epsilon minus 1 minus 2 times 2 a2 is equal to 0. And we can get a pattern. And finally, if I just take any q to the power I for a general term, and that is going to be I plus 1 multiplied by I plus 2 a I plus 2 plus epsilon minus 1 minus 2 times I a I, and that is equal to 0. So this is the general term, and this leads directly to the recurrence relation. And the recurrence relation in this particular case we get is equal to some a I plus 2 is equal to minus of epsilon minus 1 minus 2I, and this is I plus 1 I plus 2 and a I. So this is called the recurrence relation. So this is Ray C U R R E N C E, recurrence relation. Correct. So this is the recurrence relation which connects AI to AI plus 2. So if we know A0, then we can get A2, and then from there we can get A4 and 6, 8, all the even A's. And if we know A1, then that will lead to A3, 5, 7, etc. So therefore, we need to know a0 and a1. They are going to be independent coefficients, and once we know a0 and a1, the rest of the coefficients are just going to be given by this recurrence relation. Therefore, what we get is that there are only two independent coefficients, that is going to be the a0 and a1. So a0 and a1 are going to be independent coefficient, and that these two independent coefficients will give to all the other coefficients from this recurrence relation. Okay, so here we end the lecture 1 on simple harmonic oscillator. We'll in the next lecture we'll continue from here, and we'll check that this infinite series f that we have got along with this particular recurrence relation, how this particular series behaves when we have infinite number of terms, and whether that is going to be an acceptable solution or not. So that will continue into the next lecture. Till then, it's bye bye from me.